Hi everyone, welcome to this video, and today we'll be going over how to sketch Bode plots with respect to transfer functions of any process control system. So let's dive into question number one, and we'll start actually with a couple of quick questions in terms of finding the amplitude and phase of complex numbers, since today will come in handy and important in solving the upcoming questions and in general dealing with frequency domain analysis of process control system and transfer functions. So let's start with the question number one. It's simply stating find the magnitude and phase of the following numbers in the simplest forms. So essentially these numbers are in both cases of A and B are complex numbers with fractions which both numerator and their denominator have complex values. Right now, we're interested into simplifying that into finding the magnitude and phase of the whole fraction. An easy way to do that is to simplify this question into two parts of first finding the magnitude of each one of them. So let's start with the first case. Let's call it A. So we know that for a fraction, if A is composed of any kind of fraction such as b over c, for instance, that both b and c are complex numbers, in that case, magnitude of a is simply the magnitude of b divided by magnitude of c. However, the phase of a becomes the phase of b minus phase of c. So that's how actually we will be dealing with finding the magnitude and phase. So let's get started actually with the first one. So if our fraction is going to be 2j plus 1 divided by minus j, then the magnitude of a simply becomes the magnitude of 2j plus 1 in the numerator divided by magnitude of minus j in the denominator. The denominator is simply minus j, which has the same magnitude of plus j, which is a simple complex number that has a magnitude of 1, because the coefficient of j is only 1. So we simply can call it 1. Numerator, by the way, is composed of a plus jb format, that if you want to find the magnitude of that, we need to square root of both of them and then sum them up and then take the square root of them. In that case, we need to write down 2 to the power of 2 plus 1 to the power of 2 under root squared, and that takes us to a value of around square root of 5. And if you simplify that, we would get to 2.23 if you want to round them up to 2 decimal places. Now, in terms of the phase, by the way, or the angle of this complex, so we need to find the angle of 2j plus 1 first as the numerator, and then subtract the angle of minus j from that in order to find the angle of A. The angle of 2j plus 1, by the way, if we think about sketching that on the complex plane, 2j plus 1 is simply has a real part of 1 and an imaginary part of 2, so our dot is located over there. In that case, we can simply create a rectangle such that this rectangle is composed of this real number and imaginary number, and the angle between these two sides is going to be called the theta that we're after that. For this theta, we need to know that the tangent of that is equal to 2 divided by 1. So essentially, this angle equals tangent of this theta equals 2, which means that theta equals tan inverse of 2. So we can easily write tan inverse of 2. Let's take a look at the next one, minus j. So if we locate minus j on the same complex plane, we'll have minus j here, which is sitting here. And if you want to find the angle all around here from the horizontal axis, we'll need to consider 270 degrees indeed, or minus 90 degrees, and both of them are equal, since if we add or subtract 360 degrees to any value of phase, uh, we won't change the phase. So essentially, the value of phase for that is going to be minus 90 degrees. If you calculate uh, tan inverse of 2 using the calculator, we will get to value of 63 degrees. And minus 90 degrees, it equals plus 90 degrees, which takes us to around 153 degrees. So that is the angle of this whole complex number. So in simple term, A is our complex number, can be represented as 2.33 as the magnitude with an angle of 153 degrees. So that is the first part of this question. The second part of the question has a little bit more complex uh, magnitude and phase format. So let's get started with that. Imagine again, we're going to have that as A. Now, A, in terms of the magnitude, similarly is going to be represented as square root of the real part squared. So 3 to the power of 3 plus the imaginary part squared minus 3 to the power of 2 divided by, again, the real part to the power of 2 plus the imaginary part minus 1 to the power of 2. So let's simplify that. So the numerator will become 3 square root of 2, and the bottom denominator will become square root of 5. And if we simplify this, we will get 1.89 as the magnitude. However, for the phase, we need to consider the phase of A to be the phase of 3 minus j3 as the one coming in the numerator, minus phase of 2 minus j. So let's try to find the first phase first, the phase of 3 minus j3. So it's easier for us to start plotting that on the complex the plane. So we'll have the real part as 3 and imaginary part as minus 3. So our point is going to be located here. And in terms of the angle, we need to find out the angle from the horizontal axis all the way from there, horizontal axis to this point. However, an easier way to find the angle is going to find this theta prime instead of theta, because theta prime is going to have an angle lower than 90 degrees, and it's easily calculatable with a calculator. In order to do that, we try to create this triangle, and this triangle then helps us to find the angle of theta prime simply with respect to the fact that the tan theta prime is simply 3 divided by 3. So we know that tan theta prime is going to be 3 divided by 3, and that's 1, which means that theta prime is going to a tan of 1, which is 45 degrees. But then 45 degrees is only theta prime, and we need to consider theta, which is essentially 360 degrees minus 45 degrees, or it is minus 45 degrees. So we'll use minus 45 degrees for simplicity. So that's the angle of the first part, minus 45 degrees, minus the second one. The second one is going to be treated the same as well. So I'm going to I'm going to actually move it around a little bit and resize that just to be able to create another diagram of complex number. And then the real part again, this time is going to be 2, the real part, and imaginary part is going to be minus 1. So the real part is going to be 2, the imaginary part is going to be minus 1 or minus j. So our point is here. In order to find the angle, we need to calculate the whole theta like this. However, there's an easier way, as we just discussed, is to find a theta prime in this case again, because calculators are good with calculation of the angles lower than 90 degrees. And this can be easily calculated with respect to theta prime as follows. So we know that tan of theta prime in the second case becomes now the imaginary part 1 divided by 2. Remember that in this case is actually we haven't used negative value for 1 simply because we're only dealing with this small triangle, and we know that this angle now doesn't depend on the value of the sine of this length. It only depends on the value of this length or the magnitude of it. The sine is later going to be attributed with respect to theta. So tan theta prime will always deal with positive numbers, both in the numerator and denominator, and that's the beauty of using these sketching. So if you simplify, so if you calculate uh, theta prime to be a tan of 1 over half, we would get to a value of around 26 degrees. However, we know that the relationship between theta prime and theta is either theta prime and theta are going to sum up to 360 degrees, or theta prime is going to be negated in order to get theta. So I'm going to use the negative value of 26 degrees in this case. So again, it's going to be minus 26 degrees. And with this color code, you would clearly see that this angle is going to be representing the numerator, and this angle is going to be the numerator. So simply, we can then sum them up as follows: minus 45 minus 26 degrees, it'll be plus 26 degrees, and that would take us to 19 degrees with a negative sign. So essentially, this whole value of a in this second case is going to be, with respect to its magnitude, 1.89, and the phase of it, which is going to be minus 19 degrees. Okay, so let's dive into second question, which is indeed how to plot the Bode plot of a given transfer functions with respect to different parts of it in terms of different zeros and poles, or a constant number as its coefficient. So I'm going to explain the generic procedure which can be applied to any kind of transfer function. And in this case, this transfer function is almost considers all of um, this transfer function And this transfer function almost considers all of the possible scenarios for the zeros and poles and negative numbers as a coefficient, and all of them. So it'll be a complete example. So first off, we need to break it down into simpler pieces. But in that conversion process and simplifying and factoring it out into simpler pieces, we need to be mindful of the fact that it would be easier for us to uh, demonstrate both numerator and denominator in terms of 1 plus s over a as one of the coefficients, whether it will be a pole or a zero, because it's only in this case that we can have a as the pole or zero, depending on whether it shows up in the numerator or to represent a zero, or denominator as a pole. So in that case, a can be easily can represent the frequency of a pole or zero. In this case, we call that as the critical point. And in order to get that done, if the denominator of s is not going to be a, and the summation is not going to be 1, we need to factor out from that constant value to get to a constant of 1. So with that perspective, let's simplify this. So we have s plus 6 in the numerator, and as you can see here, the constant is not 1, so we have to factor out from 6. So this simply becomes 6 times 1 plus s over 6 in the numerator. And then we can keep this constant number as the same as it is. So minus 600k. So minus is going to multiply by 600,000. The numerator, by the way, will have s, which shows up itself as it is. And we also have another factor as a pole that the constant is not 1. So we have to actually factor out this constant, which is 100k. So in that case, we can have 1 plus s over 100k. And then we can multiply 100k outside. Now, if we simplify this 100k with this 100k of 600k, we can further simplify that. So now if we simplify this 100k from this 100k of this 600k, we can further simplify this whole scenario as follows. So it'll be minus, in that case, 6 is going to be multiplied by 6, which is going to be 36. So minus 36 times 1 plus s over 6. In the denominator, we'll get rid of 100k. We'll have only s times 1 plus s over 100,000. So essentially, this will be our final simplified transfer function. In order to get this done, I'm interested into simplifying that a little bit further, simply because we have different parts of this transfer function as I'm scoring them. So you can see that we have 5 segments of that. So segment 1, 2, 3, and 4, and 5. 3 of them appear themselves in the numerator and 2 of them in the denominator. However, we need to separate them in this manner so that we can plot them separately and then add them up. And I'll show you how to add them up in general. So starting with the first one, so this minus sign actually, or minus number, doesn't add anything to the magnitude because its magnitude is 1. So in terms of the magnitude, we won't consider this in general. However, it'll show up itself in the phase, which we'll discuss that in the next slide. So in terms of the magnitude, we'll start with this 36. And we already know that for this, to consider number 2, I will just write 2. We need to consider what would be the 20 log of 36. And if you simplify that, you would get to a value of 31. So we need to deal with 31 dB as the constant number because it doesn't depend on the frequency, as the magnitude of 36, or part 2. For part 3, we need to consider this magnitude of, so let's plot part 2 first. So part 2 just gives a constant number. So I'm just drawing the constant number of 31 dB. Hope that it becomes roughly 31 dB across the whole frequencies. So let's move on to the next part, part 3 of this transfer function, 1 plus s over 6. So for part 3, we know that 1 plus s over 6 demonstrates as 0. And in this case, the transfer function has the 0 at the frequency of 6. So omega equals 6 is going to be our critical point number 1, because that's the 0 of this transfer function. And in that case, we just need to find the location of 6. So this is going to be a frequency of 6, roughly, with respect to the magnitude frequency of 1. And I'm going to actually draw a rough line over there that demonstrates roughly where 6 is. And this helps us find the cutoff frequency of this 0. So let's try to plot the frequency response of this 0. We know that for the zeros, we will start from 0 dB all the way to get to this critical frequency. And after that, we will start at 20 dB per decade increasing in the magnitude. So this will be the generic form of a 0. So let's try to find the 20 dB per decade. And 20 dB per decade means that after 1 decade, which we'll get to around here, we need to go 20 dB above. So each one of these vertical or horizontal lines are 20 dB apart. So we need to just connect all of these dots together to get there. So I'm going to draw that roughly. uh, So it'll be around here. This would represent actually our part 3. Now let's move on to the denominator, part 4. So part 4 is essentially 1 over s, which is the 0, which is the pole of this transfer function at the frequency of 0. We can easily identify that the magnitude of this 1 over s becomes 1 over s in absolute value, but then this magnitude is going to change at all frequencies uniformly with a same slope of minus 20 dB per decade. And essentially, since the pole is going to be 0, the critical point of this is not going to be shown on this horizontal axis, because 0 frequency is going to be significantly small in value. We can't even demonstrate that on this Bode plot, since this is logarithmic scale, and in the log scale, we don't have any 0 in the log domain. So it'll be very, very small value all the way towards the left, but then we don't have that critical point visible on this Bode plot. However, we can make use of a feature of this portion of the transfer function, and that is this magnitude can be calculated at any point of interest, because this simply represents a single line. So for a line, we just need to know a single point of it and its slope. We already know its slope because the slope is minus 20 dB per decade. And the value of 1 point can be simply represented as what would be the value of 1 over s at any frequencies. The easy frequency value for this would be s equals to 1, because it's at s equals 1, the magnitude of 1 over s becomes 1, and 20 log of 1 becomes 0. And that takes us to 1 point, that is 0 dB at the frequency of 1. So if we recognize the frequency value of 1, we should be able to actually get to 0 dB at that, only due to 1 over s. But then this is only 1 point of this line. We need to consider the slope as well. The slope is going to be minus 20 dB per decade. In that case, it's going to be roughly on this line. I didn't draw actually perfectly, but eventually I'm trying to actually draw that with a different color. So if I try to identify the other points as well, they will be sitting around here. So if I connect all of them together, we'll have a straight line that is passing through all of those lines, and specifically from this frequency of 1 and the amplitude of 0 dB, with the slope of minus 20 dB per decade. So that is how 1 over s is going to be represented. I'm going to just point at that here, and that is 1 over s, or essentially part 4 of this question. So now that we're done with that, let's move on towards the final segment of this question, and that is the another pole, which is sitting at 100K, because 100K is going to be the value under S, so that is the pole in this case. So segment number 5 is going to have a pole as 1 over, going to actually write it with a black, 1 over s plus s over 100k plus 1. And essentially, the generic form of this transfer function is going to first identify 100k. So that is our critical point. 100k is around here. And once we identify that, we need to be mindful that all of the lower values in frequency is going to be 0, and higher values are going to be minus 20 dB per decade. So that is the generic form of the pole. So 100k on this line, I'm going to draw that with another color of green in this case, and another 20 dB per decade, which is going to be around somewhat like this. Now, we're done actually on all of the different parts of the question. Let me also call this as this guy, which is number 5. Now, we're done on the individual segments, and we just need to sum them up with respect to different critical frequency points. So I just drew the critical point of 100k as well here. So with respect to these two critical points that we had as the two zeros and poles, we need to sum the transfer function of individual blocks together. So starting from the lower value or low frequency, we see that these overlapping or any other so starting with the lower value of frequency, we know that these points are going to be 0. However, this 31 dB is going to have a constant uplift of all of the transfer functions. And also we have a line with a negative 20 dB per decade slope. So from very, very low frequencies up until this critical point, indeed this critical point. So from the very, very low frequencies up until this critical point, we need to follow the same trend. We need to just sum this 30 dB with these 0 dB, and also that shifts up the minus 20 dB per decade line by 31 dB. So imagine that this line is going to be shifted up by 31 dB and is going to appear here just because of the constant value of 31 and 0 dB of the other two transfer functions. So let's try to start working on that. So 31 is going to be increased by 20 dB. It's going to be 51 dB. And then the easiest way is to find what would be the amplitude here in this critical point. We know that at this value, the value of so in order to find in order to find out that at which point of amplitude this line is going to hit the frequency of 6, we need to just reduce the amplitude with a slope of minus 20 dB per decade, and it would be around here roughly. So I'm going to roughly draw that to around here. Okay. So now that we're done on this, we need to consider what is the change that we just started to see in our diagram. So this minus 20 dB per decade is not changing after this critical point. Similarly, for this pole, we don't have any change. And also this constant number doesn't change at all. However, the only change is only for this 0. This 0 was initially showing a 0 dB. However, right now we're dealing with positive 20 dB per decade increase in this line. So if we consider this positive 20 dB per decade plus this constant, plus this a constant, and plus this negative 20 dB per decade, we can easily see that this 20 dB per decade is going to be canceled by this minus 20 dB per decade. So right now, we just need to find out what is the change in the slope of this diagram, because the absolute value is already determined and locked in with respect to this initial point and this slope. So this absolute value is not going to change, but the slope of this curve after this point is going to be determined by the slope of the next set of curves. Right now, that these two are going to cancel each out, it means that the slope is going to be 0. And then how long it's going to uh, keep this trajectory until the next critical point, which is here, because up until then, none of the slopes are going to change. So essentially, we're going to have something like this straight line for the between these two critical points. Now, again, we know that the magnitude of this point is locked in, and that's accurate. But then, what would be the angle and slope of the next curve? So we need to know that what is the change that we just started to see, and that is the only presence of this pole that introduces another negative 20 dB per decade to the slope. So the slope currently was 0 dB. And with this additional minus 20 dB per decade, we're expecting to have, and again, a minus 20 dB per decade of slope. So it will be roughly around this line. So we can see that how the magnitude of the Bode plot is comprised of summing up of individual Bode plots of the zeros and poles and constant values. We've considered part 2, part 3, part 4, and part 5 as 4 different transfer functions, and then summed them up with respect to critical points that we had. Because only in the critical points we introduce new slopes to the main transfer function Bode plot. So that's it for the magnitude. Let's move on to the phase diagram in the next slide. So now let's try to focus on the phase diagram of this Bode plot. I have copied the same transfer function here with the same decomposition into different parts. And now we're going to again deal with it the same way of trying to draw the transfer function of the phase of each one of them separately and then summing them up. So starting with the 1, we know that for 1, we have the negative sign, and the angle of -1 is going to be a constant value, and that is going to be minus 180 degrees. So, and it is exactly the same as plus 180 degrees because we can always add or subtract 180 degrees to any phase value. Now, we can consider that as a constant value across the frequency to represent -1. So I'm going to actually show that this is for -1. Now, let's move on to the second one, as the second one is 36, but the angle of 36 is going to be 0, so it's not going to add to any phase, and that's why that we're not considering that. So let's move on to the third one, which is our 0, and that is going to be 1 plus s over 6. And we know that at omega equals 6, we have 0. And the generic form of the phase diagram for the 0 is such that the phase is going to be 45 degrees at the frequency of interest. And at this point, I already have demonstrated the first critical point at the frequency of 6. And we know that since this is phase, the phase is going to be 45 degrees at that point. So let's try to call it as 45 degrees with a dot. And then we know that 1 decade above and 1 decade below that, we're going to have phase of positive 90 degrees and 0 degrees respectively. So it'll be something like this in general. it'll be 1 decade after that, we have 45 degrees higher, and 1 decade before that, we have a 45 degrees lower angle in phase. So you're almost dealing with these two values roughly, and we can draw the rest of the diagram like this. Now, so that's pretty much it for the third one. Let's move on to the fourth one. The fourth one is going to be 1 over s, which is the denominator. And 1 over s, in terms of the phase, is going to, the phase of 1 over s is essentially the phase of 1 over j omega. And you can see that we're dealing with a 1 over j, which is the same as minus j. So the angle of minus j is going to be minus 90 degrees all the time, regardless of the value. We have a constant angle of minus 90 degrees that covers the whole range. So I'm going to actually draw that here as well and just show that this is for 1 over s. I forgot to write what this refers to. So this is essentially 1 plus s over 6. Now let's move on to the fifth and final one. And the final one is 1 plus s divided by 100k. And then that's in the denominator. So essentially, the phase diagram for this pole is going to be represented by, again, the critical point of it, which is going to be 100k. And at that critical point, the phase is going to be minus 45 degrees in this case, because that's a pole. And 1 decade before that, the angle is going to be 0, and 1 decade after that, the angle is going to be minus 90 degrees. And we're going to deal with something like this. So I'm going to actually draw that with a black line so that actually would be clearly visible. So at 100k, we're going to have minus 45 degrees, and 1 decade before that, we will have 0 degrees, and 1 decade after that, we'll have minus 90 degrees. So let's connect them together like this with a straight line, and then the angles are going to be like this. So let's also try to call that as 1 over s plus 1 plus s over 100k. So that's it for all of the individual compartments of these transfer function. Now we're trying to actually add all of these 1, 2, 3, 4 phase diagrams together, because we didn't consider the second one since that didn't contribute to the phase. So we just need to add all of them up, and we need to also consider at which points these slopes are going to change indeed. We know that this slope is positive 45 degrees per decade, and this slope is minus 45 degrees per decade. However, uh, before the start of this initial 0, or 1 decade before 0, we would have the same value of phase, which can be represented as 0 plus minus 90 degrees plus minus 180 degrees. So essentially, if you sum them up, you get to the value of minus 270 degrees. So I'm going to plot that with a red color. So up until 1 decade before the 0, which in our case, 0 is 6, but 1 decade before that is going to be 0.6. So 0.6 is going to be the new critical value in the phase diagram. And we're now going to have 45 degrees per decade increase in the phase, because this is going to be represented and introduced to the system due to this 0. The other phase diagrams are still constant, and they are not going to change their value after this 0.6. However, there is only one curve that adds to the phase at an additional 45 degrees per decade. So we will have 45 degrees per decade increase up until we reach another. Uh, so that's how pretty much this will work. After one decade, we increased 45 degrees, and another decade, we increased another 45 degrees to get to 90 degrees of total change. And now is the time to see that what are the new changes in the slope. So this change is 0, this change is 0, this change is 0, this change is 0. It means that we are going to actually experience a 0 dB per decade, or zeroth angle per decade, for the rest of the phase diagram, up until this point where the angle changes. So until this point, we will have phase of 0. Now we know that this minus 45 degree per decade is going to add to the phase of this final transfer function phase. And the other diagrams, the other zeros and poles are not going to contribute. So we will follow only this. Since this is minus 45 degrees per decade, we will have also minus 45 degrees per decade up until we reach here. So we'll have something like this. Now, after this point, because the angles are going to change their slope, if we sum all of these slopes together, we won't get actually any change in the slope. So it will be a 0 degree per decade for the rest of the transfer function. So essentially, the whole phase diagram is going to be somewhat similar to this in general, as we sum up individual blocks of the original transfer function. We need to also be mindful of the fact that when we are adding together all of these phase diagrams as well as this magnitude diagram, the final transfer function is not going to be this type of piecewise linear, but eventually they will merge together, and in the merging point, we're going to actually deal with a sort of a curvature, as you can see here. So it's not a piecewise linear anymore, but if we try to actually connect them together, we're going to deal with something like this. And essentially, this happens for the phase diagram as well. If we connect all of them, they are going to be smooth variations in the phase diagram as well as magnitude diagram of any Bode plot. That is mainly demonstrated in the Bode plot that I have plotted in MATLAB, and that is with the absolute accuracy that we have had. As you can see here, it started from a value of around 1 dB, and it goes down with minus 20 dB per decade, then 0 dB per decade, and minus 20 dB per decade again. And you can see that the curvatures that we have over here, similarly for the phasor diagram, we have the same. You might wonder that why the phasor started from 90 degrees versus ours, which has started from minus 270 degrees. Again, if we add or subtract 360 degrees to the phase, it wouldn't change any major part of the phasor diagram. So essentially, both of them are correct. So that's it pretty much in terms of the plotting of the Bode diagram. So let's move on towards the last question. So the last question is asking, a single stage low pass filter needs to provide an attenuation factor of 25 for a 60 hertz signal. So that's the characteristics of a low pass filter. Part A of this question, which has like many parts, is asking, draw a low pass filter with a resistor and a capacitor. And we know that we can plot different types of filters with different electrical elements such as resistors and inductors, or resistors and capacitors, or with the help of an op amp. But in this case, it's in the simplest form of plotting it with a resistor and a capacitor. And so let's get started. If we consider a low pass design would have R and C combination like this, and if you want to call V out um, across the capacitor and V in across the whole diagram, then in that case, at very low frequencies, this capacitor is not going to act, and it will be open. So in that case, the input is going to be completely transferred to the output. However, at very high frequencies, this capacitor is going to be short-circuited, and the output is going to be zero. That's how this represents a low-pass circuitry. The next part of the question is saying, try to find the Laplace transform of the resistor. So we know that resistor is represented as a V over I. However, the resistor in this case is a constant value. And the transfer function of a constant value in the Laplace domain is going to be, again, a constant value. So it doesn't change. The next part of the question is find the Laplace transform of the capacitor. So we're working towards finding the transfer function of each element in the frequency domain. So we know that I equals C dV over dt, as the question itself suggests. If we convert them, both sides of them, into the Laplace domain, or take the Laplace transform from both sides, I in the frequency domain becomes then C, which is a constant, times dV over dt in frequency domain becomes S times Vs. So there is a factor of S, which is going to be multiplied by the transfer function of V. However, in a more complicated format, we need to consider that we have an initial condition of minus V0. That is going to be considered with respect to this dV over dt. So this V0 is the initial condition of the voltage of a capacitor in this case. So if we assume that there is no initial condition in this case, and we simplify this, therefore, what we have is essentially IS equals CSV. And if you want to actually represent VS over IS, this which is essentially the resistance or impedance of this element in frequency domain, then we will have 1 over SC. So this is the transfer function of a capacitor in the frequency domain, or essentially its Laplace transform. So let's move on towards the next question, which is find the transfer function of the filter. So let's redraw the diagram one more time, as we know that C and R are represented as follows, and the input and output are going to be as shown. And in terms of GS, which in this case is talking about V out divided by V in, we need to also replace C and R with their Laplace transforms. And we know that C is represented by 1 over S, R is represented by R. So if these substitutions are going to be used, we know that this impedance is a simple voltage division across the whole input impedance. So only a portion of the input impedance is going to be delivered to the load, but that portion is simply the impedance of the output or the capacitor, which in this case is going to be 1 over SC, divided by the total impedance, which we have R plus 1 over SC. So that's simple voltage division structure that we are dealing with. And if you simplify this, we have RCS plus 1 and then 1 in the numerator. So that is the transfer function of the whole filter. Now, the next question is an interesting one indeed. It's asking, calculate the resistor size required if a 10 microfarad capacitor is used in the RC circuit. So we need to actually go back to the question itself again, when it was asking uh, that the attenuation factor that is given in this question is 25 at a frequency of 60 hertz. So we'll make use of them here as well. So attenuation factor is going to be 25, and the frequency is going to be 60 hertz. Now, we need to understand the fact that when they're talking about the attenuation factor, it's the amplitude reduction of the whole function. So in this case, GS in amplitude is going to be 1 over 25, because that's how the attenuation factor is representing. That means that the amplitude of the signal is reduced by a factor of 25, and GS is representing that with a 1 over 25, because that's the attenuation and it's not amplification. So magnitude of 1 over 25, we need to equate that with the magnitude of GS. So what is the magnitude of GS? So the magnitude of GS is simply 1 over square root of RC omega squared plus 1, simply because S equals J omega. And omega is simply 2 pi to the frequency, which in this case is, this frequency is 60 hertz. So that's how they are related together. And we already know that this equation can be further simplified as 25 equals RC omega squared plus 1. So if we take the square of each side of this equation, it would be 625 equals RC omega squared plus 1. And in order to solve for resistor, we have RC omega squared equals 625 minus 1, and RC omega, because we know that all of these are non-zero and positive numbers, is going to be square root of 624 in this case. And we know that C then becomes 10 microfarads, because that's already given in the question. So we are going to actually make use of that here. It'll be 10 microfarads, or 10 to the power of minus 6, times omega, which we just found that here, 2 pi f, with f being 60 hertz. So it will be 2 pi times 60. I'm going to then multiply that by r. So let me just highlight these so that it would be r as this one. It would then be c, which is this value. And finally, when we have omega, it is essentially this value that are going to be multiplied together. And we can see that we can easily find out r with simple division. And if you simplify this, you get to the value of r equals 6.6 K, or kilo ohms. So the next question is asking, plot the frequency response in the next page after populating the table. So I'm going to actually show you how to find out the missing parts of this table, and then leave the last question as an exercise. So you can see that over here, it's talking about a frequency in radian per second. So imagine that this represents omega in this case. That's radian per second. It's not a frequency in hertz. The gain in dB is demonstrated here, and the phase in degrees is demonstrated next to that. So with that, let's actually rewrite the equation of GS that we had in the previous question. So we had 1 over RCS plus 1 And we know that R value is going to be 6.6, K or 10 to the power of 3. And the capacitor is going to be 10 microfarads or 10 to the power of minus 6, S plus 1. So if you simplify that, you get to the value of 1 over 0.066 S plus 1. So if you want to actually find the magnitude, then the magnitude of GS is going to be 1 over square root of 1 plus 0.066 omega squared. Since we know that we're given actually the value of omega over here, so we can easily plug it here to get to the value of the magnitude. But as you can see here, this is only the amplitude of that. If you want to find the dB format of this, we need to know that G in dB is simply 20 log of GB GS in the amplitude format or the magnitude. So that's for the gain in dB. For the phase though, for the phase of GS, we know that the phase is going to be composed of phase of numerator, which is phase of 1, minus phase of denominator, which is tan inverse of denominator. And denominator is simply 0.066 omega times J, and numerator is 1, in real part is 1, so this is the arctan of this value is going to be the phase of the denominator. So we know that phase of 1 is 0, and the rest is going to be simply minus angle of, or minus arc tan inverse of 0.066 omega. So that is how we can find the phase, and we need to be mindful of the fact that our calculator should be calculating everything in degree. So if the first two frequencies are given, but the third frequency, if you simply try to plug 10 as omega for both magnitude and phase, so essentially for 10 would have the magnitude of J10 as we substitute J as the frequency, then we would have 1 over square root of 1 plus 0.066 times 10, which in this case it would be only 0.66 to the power of 2. So if we simplify this, you would get to the value of 0.83. And if you take 20 log of 0.83, you would get to the value of minus 1.6 dB. So that's why that we can easily write minus 1.6 over here. So that is the dB value of the gain. However, for the phase of J10, which in this case it's going to be minus tan inverse of 0.66. So if you simplify that, you would get to the value of minus 33 degrees. So simply minus 33 degrees is going to be set there. So you can keep working on this table and populate the rest of the blank spots with respect to the magnitude and phase according to the procedure that I just explained. With that in mind, the last question that it's asking, I'll plot the Bode plot of this function. I'll leave it at as an exercise to you guys to find that out. So essentially, it's asking to essentially plot the Bode plot of this function which is 1 plus RCS, which is 0.066 S indeed. So that's a simple pole that you need to plot. It's a Bode plot. So let's leave it at that. And thank you for your notice and attention. And if you like this video, please subscribe to this channel and hit like to get more videos in the upcoming days. Have a good one.